What's up, guys? It's Mr. Brangle, and today we're going to be going over a VIRP chart for a combo circuit, or otherwise known as a complex circuit. This is going to be a combination of a series and parallel circuit, and hence the name combo circuit. So what distinguishes a combo circuit is that it has features of both series and parallel, and we can see this resistor right here. This resistor is wired in series, so there has to be one or more resistors wired in series. And the way that we know it's wired in series is that every single electron would have to pass through this light bulb no matter what, right? So if we think about going this direction or going this direction, this is either before the split or after the split on the way back to the battery. Regardless of which way you look at it, every electron must go through this light bulb. Same thing would be true over on this side of the circuit. So anything up here would be wired in series, or anything over here. Once electrons get to this point, it branches, right? Some electrons go this way, some go this way. And then they would join back up on the other side. So these two are wired in parallel because not every single electron has to go through those resistors there, or those light bulbs. Okay, so what I like to do to start off with is I like to label, I write out all my resistors over here, and I'm going to label this one is in series, and then this one is parallel, and this one is parallel. And I think it's really, really important that you keep those things straight. So the first thing that we have to do is find the total resistance of this circuit. But to find combo resistance, the way that we're going to do that is we're going to have to first calculate series resistance, and then we're also going to have to calculate the parallel resistance, and then we combine them to get the combination resistance. So for a series, for series resistance, we would just add up all of the light bulbs or resistors in series. In this case, there's only one of those types of light bulbs, and so the series resistance is just 3 ohms. And I'm going to go ahead and write that here. That's why I skipped a line for the total voltage. I'm just going to write 3 ohms right here, and then I'm going to put the parallel resistance right here, and then down here we will write our combo resistance, which would be the total resistance of the circuit. So this is step 1 right here. The parallel resistance, we'll use our parallel resistance calculation, or equation rather. So 1 divided by, and then in parentheses in the denominator, it's 1 over each branch resistance. So 1 over 1 ohm plus 1 over 4 ohms. Okay, and when I plug this into my calculator, and you should do the same thing, pause the video if you need to, make sure you get the same answer. This should come out to be 0.8 ohms. Okay, and I should probably go ahead and box this one in as well. So, whoops, wrong spot there. Put this in over here. So 0.8 ohms. Now, all we have to do, step 2 here, to get our combo resistance is simply add the series and the parallel resistance together. So that's obviously going to be 3 plus 0.8, which is going to give us 3.8 ohms of total resistance in this circuit. So again, calculate your series resistance by adding up all of the series resistors. Then calculate parallel resistance using the equation for parallel resistance, and then add those two things together to get your combo. Okay. So I better label this as step 2 here. And now we will go on to step 3, which is going to be total current going through the circuit. And just like any other circuit, total current is going to be total voltage divided by total resistance, or in this case, the combo resistance. So this is going to be 9 volts divided by 3.8 ohms. And this is going to give us 2.37 amps. And again, make sure that you're using a calculator. Don't, if you were absent or what have you, and you're doing this for the first time, check my work. Make sure you're getting the same number. Practice it. So 2.37 amps right here. Okay, so now the next thing that we need to do is start evaluating rules, right? So There's obviously different rules for current in series than there is for parallel. We know in series the current should be the same everywhere, and then in parallel the current will split up into the branches, and when you look at the current on individual branches it should add back up to your total. So those things are still going to be true here. If we go to any resistor that's wired in series, the total current in the circuit should be going through that light bulb or resistor. So the fourth step here would be up here on our series resistor, going ahead and entering the total current in the circuit. Okay, so this is step 4. Current equals same. And then in parentheses, I'm just going to put series. Okay, we're going to actually calculate the current that's going through each branch of the parallel circuit, but we can't yet do that. We first have to figure out voltage drops. And you're going to want to calculate the voltage drop of the series resistors first. Always do that. That voltage we're going to subtract out of the battery. Whatever voltage is left over is applied to the parallel portion of the circuit with the same rules that we would typically have for a parallel circuit. So let's go ahead and just walk through that. Voltage here is going to be equal to current times resistance for this series resistor. So this voltage drop at the 3 ohm resistor will be 2.37 amps multiplied by 3 ohms, the value of the series resistor. So this is going to give us a voltage drop of 7.1 volts. And we'll go ahead and fill that in right here. Now, think about it as if that voltage from the battery, 9 volts total, 7.1 of those 9 volts are used up to get through that 3 ohm resistor. So we have 1.89, I did some rounding here, but 1.89 volts will be left over. That is then applied to the parallel portion of the circuit as if it was just a parallel circuit with these 2 branches and a 1.89 volt battery. Okay, and if you wanted to put 1.9, obviously that's fine too. I try not to round in my calculator, but on here it's okay. So I'm going to go ahead and put 1.9 volts for each of these. So this is I'm going to kind of combine these. This is step 6 right here, is understanding this part, and this is one of those things that I feel like people kind of have a hard time understanding, but whatever voltage is left over after the series voltage drops is what's applied to the parallel portion. So I'm going to write VP for parallel voltage is equal to, and then in parentheses I'm going to write V total battery voltage minus VS for series voltage. So this is going to be 9 volts minus 7.1 volts, and that's where we get the 1.9 volts for the parallel portion of the circuit. Okay, and remember, in a parallel circuit, the battery voltage is applied to each branch of the circuit. So if you had a 1.9 volt battery and 2 branches, each of those, and 1 light bulb on each branch, each of those light bulbs is going to drop 1.9 volts. The only way that would not be true is if you had multiple light bulbs on a branch, and then they would add up to 1.9. Okay, I'm going to go ahead and move my screen up here. All right, so now that we have that, we can now calculate the current going through each branch. So that's going to be step 7 right here, is these 2 boxes. And current going through each branch is going to be equal to voltage divided by resistance. And again, that's for each branch. So I'm just going to do A and B. A will be the first branch with 1 ohm of resistance, and then B will be the second one. So current A is equal to 1.9 volts divided by 1 ohm, which obviously I'm just using these numbers here, right? 1.9 volts divided by 1 ohm, 1.9 volts divided by 4 ohms here. Okay, so obviously this is 1.9 amps. And then current B 1.9 volts divided by 4 ohms. This comes out to be 0.47 amps. Okay. So now we can check our work. Do those add back up to 2.37? And yes, they do. So that 2.37 amps of total current in the circuit is the current that's going through the series portion. So that's up here. Then it gets to this point right here and it splits up, and 1.9 amps go this way and 0.47 amps go this way, following the junction rule, right? The current going into a junction must be equal to the current going out. So there's always 2.37 amps of current that gets split up on these branches, and then it joins back up on the other side and goes back to the battery. Okay, so now that we have that, the very last step that we need to do is just calculate the power of the circuit, which is going to be step 8 right here. And this will be like our other circuits. Total power is equal to total current times total voltage. So 2.37 amps times 9 volts. And this is going to come out to be 21.3 watts. Again, make sure you check your work, or check my work with your calculator. Okay, so that is going to conclude the introduction to a combo circuit. It's obviously important that you understand the rules of series and parallel circuits before you try to do one of these. Otherwise, it would make little to no sense. So, thank you for sticking with me, and I hope you learned something.